All right, lesson 2.14, logarithmic function context and data modeling. So our skills and learning objectives here is to write a logarithmic function given two ordered pairs or a proportion and a real zero. We're going to use log functions to model proportional growth, use transformations based on the characteristics of a context or data set to model log behavior, use log regression and technology given a data set, use the natural log function to model natural phenomena, and use log models to predict values for the dependent variable. Alright, it says exponential and log functions are used to model many real-world phenomena such as magnitude of earthquakes, pH levels of chemicals, noise levels, radioactivity, and more. In this lesson, we explore many practical applications using log modeling in context to real-world data collection. And so some vocabulary and some formulas here we're going to need is we have a Richter scale model, which is going to measure the magnitude R of X of an earthquake. All earthquakes are compared to a zero-level earthquake whose seismographic reading measures 0.001 millimeters at a distance of 100 kilometers excuse me, from the epicenter. An earthquake whose seismographic reading measures X millimeters has magnitude R of X, where X sub 0 is equal to 10 to the negative 3. And so there we have that R of X is equal to log of X over X sub 0. The pH scale models a scale that measures how acidic or basic a substance ranks. The scale ranges from 0 to 14, where 7 represents neutral, and each whole pH value below 7 is 10 times more acidic than the next higher value. The H plus, the hydrogen, is the concentration of hydrogen ions measured in moles per liter. And so we can see that the pH is equal to the negative log of the hydrogen concentration. And then the last one they give on this slide is Newton's law of cooling. That's the temperature, capital T, of an object at time lowercase t, where T sub m is the temperature of the surrounding medium, and T sub 0 is the initial temperature of the object. And so you can see your formula there, T of T, so the temperature at time t, is equal to the room temperature, or the surrounding medium, wherever it's at, the temperature of what's surrounding it, plus T sub 0, so the initial temperature of the object, minus that T sub m, times e raised to the negative kt. All right, example 1. It says a satellite is launched from a spacecraft and will reach a stable orbit 300 kilometers above Earth if it reaches a velocity of 7.7 kilometers per second. Suppose a rocket has a mass ratio, R, of 26, and exhaust velocity, C, that's equal to 2.85 kilometers per second, and a firing time of 120 seconds. Use the formula for the rocket's maximum velocity, via T equals negative 0.0098 T plus C times the natural log of R, to determine whether the satellite will achieve a stable orbit above the Earth. All right, well, they gave us our formula there. So we know that V of T is equal to the negative 0.0098 T plus C natural log of R. All right, well, we know that, let's see, well, they gave us our variables with velocity, which is what we're after. Little t is the 120 seconds. So there's my little t. And our v of 120 is equal to negative 0.0098 times 120 plus C, they told me is 2.85 times the natural log of R, and the R, sorry, here, there it is, it has a mass ratio R of 26. All right, so we're just going to type that into our calculator, and we get 8.1095, and it's measuring kilometers per second. So the question is will this whether this satellite will achieve a stable orbit above the Earth. Well, it says a satellite is launched from a spacecraft and will reach a stable orbit 300 kilometers above the Earth if it reaches a velocity of 7.7 kilometers per second. This is greater than that 7.7 kilometers per second. So yes, it will. All right, example 2. The amount of energy, E, in ergs that an earthquake releases is related to its Richter scale magnitude M by the equation log of E is equal to 11.8 plus 1.5 M. On February the 5th, 2023, an earthquake measuring 7.8 on the Richter scale struck southern and central Turkey. How much energy did the earthquake release? Well, let's see. They gave us a formula. So log of E is equal to 11.8 plus 1.5 M. Remember, E is the amount of energy, and that's what we're after. M is the magnitude, and it tells me that the earthquake measured is 7.8. So M is going to be 7.8, so we're going to plug that in. So I get log of E equals, and I typed that other side in the calculator, and I got 23.5. And then we just have a log equals a number, so let's change it to exponential. So my base is 10. My y is 23.5 equals E. And so I end up with E, which is what we're solving for. So I just put that, so it could be 10 raised to the 23.5, but when I put in my calculator, it tells me 3.162 times 10 to the 23, and it's measured in ergs. So another thing on here is don't forget to label, okay? The word problems, you need to make sure you label your answers. So label, label, label. All right, example 3. The example 3 here is a little different than the ones that are in your notes. So we're going to do this because I like the table it has after it, and that way we can go ahead and decide using this table. So it just changed the pH level, and it changed the title of the chemical, the stuff that we're looking at. Okay, so instead of being baking soda and vinegar, we're going to be looking at apple juice and whole fat cream. All right, so example 3 here says the pH scale ranges from 0 to 14. A pH level of 7 is neutral. A level greater than 7 is a base. It's basic, and a level less than 7 is acidic. So it'd be an acid. So apple juice has a pH of 3.49, and whole fat cream has a pH of 6.62. It wants to know what are their hydrogen ion concentrations. So we know the formula that pH is equal to the negative log of the hydrogen ion concentration. That was given to us on the first, where we had all the three formulas. All right, so for when we're looking at apple juice, we know that it has a pH level, it tells me, of 3.49. So we know that 3.49 is equal to negative log of the hydrogen ion concentration. And so I want to solve for the hydrogen ion concentration, so I got to get rid of that negative first. I'm going to divide by negative 1. So negative 3.49 equals log of the hydrogen ion concentration. And then we're stuck, we have a single log equals a number, so we're going to change it to exponential. So the base of the log is 10 to the y, which is negative 3.49, equals that hydrogen ion concentration. And so when I stick that 10 raised to the negative 3.49 in my calculator, it tells me that it is 3.24 times 10 to the negative 4 moles per liter. All right, we're going to do the same thing. Whoops, sorry about that. We're going to do the same thing with the whole fat cream. Or whole cream. It has a pH of 6.62, so that's going to be equal to the negative log of the hydrogen ion concentration. Again, We're solving for that hydrogen ion concentration, so we're going to divide by -1. -6.62 equals log of the hydrogen ion concentration. We got a single log equals a number, so we're going to change it to exponential. So 10 to the -6.62 equals the hydrogen ion concentration. And I just plug that in my calculator so I can get it in moles per liter, and it tells me that it's 2.40 times 10 to the -7 moles per liter. All right, B says complete the table below to find the pH level and if it's an acid or a base. So remember that the pH, just like we said above here, the pH is equal to negative log of the hydrogen ion concentration. So we're just going to plug that in. So I'm going to do negative log of this number, and it tells me that it's 7.35. Remember, if it's 7 is neutral, a level greater than 7 is a base. Well, 7.35 is greater than 7, so it's a base. Then I'm going to do negative log of this number. It tells me it's 3.44. Any level less than 7 is acidic, so this is an acid. And we just keep doing that. So the negative log of 7.9 times 10 to the -8, it's 7.10, greater than 7, so it's a base. And the negative log of 1.8 times 10 to the -3 is 2.74. It's less than 7, so therefore it is an acid. All right, sound intensity levels. So this one is the same as what was in your notes. It said logarithms are used to model sound levels. The sound intensity is a measure of the energy carried by the sound wave. The loudness L is measured in decibels, dB. You can use the formula that L is equal to 10 times log of I over I sub 0. Or that's an L. I'm sorry, L over L sub 0, where L is the loudness in decibels. No, that's an I. I'm sorry. Let me try that again. So you can use the formula L equals 10 times log of I over I sub 0, where L is the loudness in decibels, I is the intensity of the sound in watts per square meter, and I sub 0 is the lowest intensity that the sound the average human ear can detect, which is 10 to the -12. Example 4 says, what is the decibel level of a normal conversation with an intensity of 10 to the -6 watts per square meter? All right, so we want the decibel level, so we want L. So we know that L is equal to 10 log of I over I sub 0. We're looking for L, so L is equal to 10 times the log of the normal conversation is 10 to the 6 watts per meter. That's our I. 10 to the -6 over I sub 0, which it tells us here is the lowest intensity sound that the average human ear can detect, which is 10 to the -12. So we get L is equal to 10 times log of, remember when you're dividing, you keep your base, subtract your exponents. -6 minus -12 is +6. And then we can just work this out. Now, there is a thing here. I'm going to show you this, okay? So one of the rules that you have the option of memorizing, but you don't have to, okay? Because we could work it out, is that if you have log base 10 of 10, if these, your base and your x base are the same, if those two bases are the same, then the log and the 10 will cancel. And so you would just get times 6. Now, if you're unsure or you don't remember that, we could always come over here. We can say log of 10 to the 6th equals y, and so b to the y equals my x, and we see that y is equal to 6 that way, okay? And so then we end up with that L is equal to 60, and it's measured in decibels. Whoops, no box. All right, example 5 says the human threshold for pain is 120 decibels. A jet engine records 150 decibels of loudness. How many times as intense is the noise of the jet engine as the noise that causes the pain? All right, so we're going to find the intensity of the threshold for pain. We're going to find the intensity of the jet engine, and then we're going to compare them, okay? So let's do it. So for the pain, the loudness is 120. And then I sub 0 we know is 10 to the negative 12. And then for the jet engine, and notice both of these equations only have an I for their variables. So we're going to solve both of these equations for I, and then we're going to compare them. So I'm going to go back to the pain one, and I'm going to solve for I. So first we're going to get the log by itself, so divide by the 10. And then I got log equals a number, so I'm going to change it to exponential. So b to the y equals our x. And then we'll multiply by that denominator to get it off bottom. And so it gives me 10 to the 0 equals I. Now we know that 10 to the 0 is 1, but I'm going to hold off on that for a minute, okay? Let's do the same thing for the jet engine. So let's get the log by itself. Change it to exponential, so b to the y equals our x. And remember, with like bases, you keep the base, you add the exponent, so 10 to the third equals I. Alright, so I want to know how many times as intense is the noise of the jet engine to the noise that causes pain, that can cause pain. So they mentioned the jet engine first. So when I go to compare them, I'm going to put the jet engine on top. So I'm going to do the jet over the pain. And so we know the jet is 10 to the third over the pain, which is 10 to the 0. And this is why I didn't work either one of them out, because I'm dividing them. And remember, when you're dividing with like bases, you keep the base and you subtract the exponents. So we get 10 to the third, which is 1,000. So the jet engine is 1,000 times greater. All right, example 6. It says an archaeologist carbon dates a fossilized bone that is thought to be around 4,500 years old. The archaeologist determines that the sample contains 60% of the original amount of carbon-14. The half-life of carbon-14 is 5,730 years. Is the estimated age of the fossilized bone correct, and explain? All right, so they didn't actually give us a formula for this, so I'm going to give it to you. So our formula is going to be the ending amount is equal to the initial amount times 1 minus the rate raised to the t, the time, divided by k. The k there is how long it's going to take to do whatever it's doing. In this case, we're talking about the half-life. So how long will it take for the half-life to occur? for that chemical, okay, or for that whatever it is. Now, when you do this, a lot of times they won't tell you a beginning and an ending amount. So you know that you can make one up for starters. So if we let our beginning amount be 1, then the half-life, half of that would be left, which would be 1/2. Or if I let my beginning amount, let's just say, be 100, then I know after the half-life there's 50 left, okay? It doesn't matter, because when you go through and you start plugging these in, and if you divide by that a sub 0, because you're going to be solving for one of the other variables, you'll end up with 1/2 is equal to the 1 minus r raised to the t over k. So if they don't give you a beginning or ending amount, you can go ahead and just pick some numbers and put in. Now the only problem here is they told me that it's 60%. So I'm not just doing the half-life, but I'm looking for 60%. So pick a beginning amount. Let's just say 100. So now I'm looking at actually this problem. This is just an idea if it was just half of it was left, okay? But here it tells us that there's going to be 60% left. So if I start out with 100 and 60% is left, then that means I have 60 as an ending amount, okay? So I'm going to go ahead and just plug this into the formula. This was just extra stuff there to think about. So I know that my ending amount is equal to my beginning amount times 1 minus, what is the rate at which this is decaying, okay, or going down? And it tells us that it is the half-life, which means the rate is 50% or 1/2 raised to the, we're looking for the estimated age, so we want to know t divided by k. K is how long does it take it to do the R. The R here was the half-life. It tells us the half-life of that carbon-14 is 5730. And so now we're just going to solve for t. So first thing I'm going to do is I'm going to get this exponential part by itself. So I'm going to divide by 100. And I end up with 0.6 equals, I'm going to go ahead and do the 1 minus 1/2, which is 1/2, or you could use 0.5, it doesn't matter. Raised to the t divided by the 5730. Now, no coincidence that we ended up with a 0.6. Because remember earlier when I was saying no matter which way you go, you'll end up with 1/2 there? Well, we had 60% left here, so we're going to end up with 60%, which is 0.6. Now, I need to solve for t. T is in the exponent. I've got the exponential part by itself, and I'm stuck. I can't get like bases, so let's just go ahead and let's do the log. So I'm going to change it to log form. Now, we've been doing the b to the y equals x each time when we solve for log. Remember with equations in algebra, as long as what you do to one side, you do to the other side of the equation, it still keeps it equal, okay? So I could do to my b to the y equals x, but then I got a log base of 1/2, and well, it's just, then I have to do extra stuff in my calculator. So the easiest way is just remember, as long as you get that exponential part by itself, what you do to one side, you can do to the other. So I can just take the log of both sides. So I could take the log of 0.6, and that would be equal to the log of 1/2 raised to the t divided by the 5730. Well, when I do that, now because I have a log, I know that this exponent can become its coefficient. So I have log of 0.6 equals t divided by 5730 times log of 1/2. And then just start solving for t. It's up to you which one you do first. I'm going to go ahead and divide by that log of 1/2. So what I get then is I'm going to get log of 0.6 over log of 1/2 equals t over 5730, and then multiply by the 5730 to get t by itself. So I got 5730 log of 0.6 over log of 1/2. And then I can just type that into my calculator, and I'll get that t is approximately 44,222.8 years. So it asked, the question was, is the estimated age of the fossilized bone correct and explained? They estimated the age to be 4,500 years old. We said it's approximately 4,222.8 years old. Is that a good estimate? I think it is. So the estimated age is close. The estimated age of 4,500 years is close to the actual age of 4,222.8 years. All right, then example 7 here says a batch of brownies are taken out of a 375-degree oven and cools to 150 degrees after 20 minutes in a room at 70 degrees. Use Newton's law of cooling to determine how long it will take the brownies to cool to 90 degrees Fahrenheit. All right, so we want to know how long it's going to take to cool to 90 degrees, but if you notice here, they give you a time already. They said it takes 20 minutes to cool above. So what it is this is almost like a two-step process. So we're going to use that 20 minutes to solve for an unknown variable that we're going to have, and then we're going to use that information to actually solve for the time it takes to cool all the way. All right, so the first thing, let's look at what they gave us. All right, so, well, first I'm going to remember my formula. So the formula for this is going to be that T of T, so the temperature at time T, is equal to T sub M, which remember is the surrounding temperature, plus T sub 0, the initial temperature, minus that T sub M, times e raised to the negative KT. All right, so looking at what they gave me first here. So I know that they're being taken out of a 375-degree oven. So when those brownies come out, they're 375 degrees. That's my initial temperature. All right, they cool to 150 degrees after 20 minutes. That's our T of T. So they're going to cool to 150 degrees. So that's the temperature at time T. So that T is 20 minutes. In a room at 70 degrees. So they're sitting in this room. That's the surrounding temperature. So that's going to be that T sub M is 70 degrees. So remember, E is just a number. So here I know everything except K. So I'm going to use the formula there to find my K. So plugging it into my formula, I know T of T is equal to T sub M plus T sub 0 minus T sub M times e raised to the negative K times T, which we said was 20. So we're going to simplify this. I'm going to subtract those, and I'm going to move this 70 over. So we get 80 equals 305 e to the negative 20k. Then I'm going to divide by the 305 to get the exponential part by itself. So I know I can reduce the 80 over 305, but I'm just going to leave it as it is. So we have 80 over 305 equals e to the negative 20k. So let's change it to exponential. Or we can do like we did on that previous problem. Remember, if we need to get that k out of the exponent, I need a logarithm so I can log both sides. And I'm going to be picky because I have a base e. I'm actually going to natural log both sides here. So I'm going to have the natural log of 80 over 305 equals the natural log of e to the negative 20k. So we're able to take this exponent and make it its coefficient. So natural log of 80 over 305 equals negative 20k natural log of e. Well, remember we talked about that if your base and your x have the same base, then they cancel each other out. They actually equal 1. So you can work it out. The natural log of e is equal to 1. So we say that cancels because anything times 1 is itself. And then we're just solving for k. So divide by that negative 20. And so k equals, type that in your calculator, the natural log of 80 over 305, close the parenthesis, divided by negative 20. And that should be approximately 0.066914. Now I went a lot of decimal places out there because this is not my final answer. Okay, this is just solving for k. Okay, so we found k, and I'm sorry, I hit something on this screen, and I just lost all the work I just did. So if you need it, you're definitely going to have to back the video up. But I can't see what I just did to when I continue here, so I'm going to have to rewrite some of it. So we just solved for k, and so what we knew at this time is we said in that part 1 that the initial temperature of the brownies was 375 degrees. We said that the room temperature, the surrounding medium, was 70 degrees. The temperature at time t, which would have been that 20 minutes, was 150 degrees. We had said t was 20 minutes. And then what we found in part 2 was that our k was approximately 0.066914. All right? So now, though it wants to know, it says use Newton's law of cooling to determine how long it will take the brownies to cool to 90 degrees. So now I want to know the time that the time it's going to take for that temperature, so the T of T, to be 90 degrees. So we're just going to use that instead of the 150 because now we're looking for little t. So the 150 doesn't count because it was the temperature at that little t of 20 minutes. All right, and so we're after the time. So we're going to use that same exact formula and we're going to plug in what we know. So now our t of t is going to be that 90 equals t sub m plus the t sub 0 minus t sub m e raised to the negative k 0.066914 times t, because that's what we're after. All right, so I'm going to move the 70 over, and I'm going to combine that right there again. So we get 20 is equal to 305 e to the negative 0.066914t. Divide by that 305. I should have just started that way up here at the top, but I was trying to start it next to it. So now I'm going to come up here. All right, so we get that 20 over 305. I know it'll reduce, but I'm going to put that in my calculator in a minute anyways. So equals that e to the negative 0.066914t. Now remember again, if I want that t out of the exponent, I just need to log both sides. And because I have a base of e, I'm going to use a natural log. So the natural log of 20 over 305 equals the natural log of e to the negative 0.066914t. And then I can take this exponent and make it its coefficient. Remember, we can work out that natural log of e. The base of E is the same as that E right there, so therefore we know it's going to be equal to 1. The natural log of E is just 1, so I'm going to 1 times the T is still the T, so I'm going to cancel that out. Divide by that negative 0.066914 to get T by itself. And so T equals, type in your calculator, the natural log of 20 divided by 305, close the parenthesis, all divided by the negative 0.066914. And we get that T is approximately 40.7176 minutes. So in approximately 41 minutes, the brownies will cool to 90 degrees Fahrenheit. So in approximately 41 minutes, the brownies will cool to 90 degrees Fahrenheit. And that's the end of part A.